Welcome again. I will present about the project that I've developed, which is the development of a safety instrumented system for the SM18 Cluster F project at CERN. So these are the topics that I'll talk about today. First, I will introduce a little bit about CERN and about our section. Then I'll talk about the Large Hadron Collider and the SM18 Cluster F project. After, I'll talk about what is functional safety and what are the challenges to implement functional safety systems at our section. Then, with these challenges, I will define what were the objectives of my studentship and what were the solutions proposed for the challenges. And I will explain how the solutions were used to implement a functional safety project for the SM18. In the end, I will present the results and the conclusion of my project. So I believe many of you already know about CERN. CERN is one of the world's largest centers for scientific research. We perform research in fundamental physics and particle physics. And CERN is an international organization which unites people from all over the world, not just physicists and engineers, but also people from almost all the areas of knowledge we have. Our section is the BICSCE, which stands for Control Engineering Section. It is part of the BIMS department and of the Industrial Control Systems group. Our goal is to provide solutions and support for the industrial installations at CERN, not for all the industrial installations, just several of them. And for those, we develop control systems and functional safety systems. The section is composed of experts from different areas of knowledge. For example, we have experts in control systems, in PLC programming, in functional safety, and in IT. My supervisor, who is here today, Borja, he's the responsible for the functional safety team, and I work with him in this topic. So the Large Hadron Collider is the most famous installation at CERN. It is the world's largest and most powerful particle accelerator. It operates in, let's say, extreme conditions in order to accelerate the beams of particles near the speed of light. So the magnets, they work in a temperature, they operate in a temperature of 1.7 Kelvin and under a pressure in the order of 10 to the power of minus 10 millibar. So these conditions are more extreme than the conditions found in outer space, for example. And the Large Hadron Collider, the LHC, will receive an upgrade, which is the High Luminosity LHC. And with this upgrade, the number of collisions will increase, and maybe we can discover new physics with this. In this context, the SM18 Cluster F project comes as the facility for testing the high luminosity LHC devices, which is the upgrade. We focus on testing two types of devices, the superconducting link and the new superconducting magnets. The superconducting link, which is this top image, is an electrical power line capable of carrying currents up to 100 kiloamps, and this supplies the energy for the magnets. And the new superconducting magnets, they have a greater magnetic field, so they can focus the beams of particles more and create more collisions. The cluster F is composed of two test benches, one for each type of device, and also it has 6 power converters to provide the energy supply, cryogenic systems to cool down the magnets and the link, vacuum systems so the particles, they don't collide with air particles, and we also have other systems. All these systems create industrial risks to our installations, and they can affect the operators and also the installations. And therefore, the Cluster F process experts, they required our section to develop a functional safety project, and this project was the main reason of my studentship. So what are functional safety systems? So according to the German organization TÜV, they are systems that lead to the freedom from an unacceptable risk of injury or damage to the health of people by the proper implementation of one or more automatic protection functions. So it's important to see that the functions need to be automatic and they target to reduce the risk of injury or damage. So basically, these are the functional safety systems. We adopt the IEC 61511 functional safety standard for our projects, at least for my projects, I'm sorry. And this standard defines the concept of safety instrumented function, which are also automatic protection functions that target to reduce the risk of one specific hazard. And then we have safety instrumented systems, which are composed of several safety instrumented functions, and they target to reduce the risk of a whole installation. In order to build such systems, the standard defines what is called the safety life cycle, which are the requirements and procedures that should be strictly followed in order to achieve the necessary risk reduction for the project. This is the image that illustrates the safety life cycle. The life cycle encompasses 11 different phases of development, and for every phase you have to create a detailed documentation and also follow the procedures strictly in order to achieve the necessary risk reduction. So there are several challenges to implement such safety life cycle at our section at CERN. First of all, the life cycle is naturally a demanding, costly, and time-consuming process. And at CERN, the experiments required large industrial installations. They are in constant evolution. So the systems are always changing, and so does the functional safety systems. So we have also to add more costs and resources to keep changing this functional safety projects. And a big problem is that our section lacks standardized documents for the different phases of the life cycle. So every project is built slightly different from each other, and we always need to waste a little bit of resource and time to figure out uh, what was the documentation created for the former project and to understand it properly in order to make the changes that are often needed. So with these challenges, several objectives were defined for my studentship. The first is to enhance the development of functional safety systems at our section in order to create a more efficient development life cycle for our section. We also aim to have a first step towards the standardization of the documents, so we don't waste unnecessary resources when applying changes to our safety systems. And last, as I mentioned before, my objective is to design a safety instrumented system for the test benches of the SM18 cluster F. So with these objectives in mind, I propose several solutions. The solutions for the safety life cycle at our section encompassed both the template creation and changes and additions of software tool in order to optimize the process of development. Regarding the templates, we followed the IEC 61511 as I mentioned before, and I created four different templates. The first one is the hazard and risk analysis, which I followed the standard to create this template. It is a spreadsheet composed of three different parts. The first part is this part on the left. It is responsible for identifying the different hazards in an installation. For that, I used the FMEA method, which is recommended by the safety standard. For the determination of the necessary risk reduction of each hazard, I used the calibrated risk graph method, which is also recommended by the standard. And the last part of the spreadsheet is for mitigation proposals. So depending on the necessary risk reduction, We can propose control systems to deal with that hazards. We can propose safety instrumented functions, which are built accordingly to the standards. And we can also propose other layers of protection. So the hazard and risk analysis gathers all this information, and the hazard and risk assessment organizes this information in one single document. This document is strictly also built according to the IEC 61511 standard. And the most important here is to describe the hazards and also to define the measures to reduce the risk. In some cases, for example, this one, we have a safety instrumented function, which has to be built according to the standards. And for each safety instrumented function, we need to specify its requirements. For that, I created the safety requirement specification, which is a phase of the safety lifecycle. And this document contains all the necessary information for this phase according to the standard. This is a quite detailed document. So for each SIF, we have usually around 4 pages of requirements. And for example, we specify what is the required response time, what is the criteria for successful operation, what are the sensors, actuators, and logic solvers that are associated to the safety instrumented function. So it's a quite detailed document, which is also built according to the standard. And the last document created is for the maintenance phase. So the standard obliges us to regularly test the safety instrumented functions. For that purpose, we have created the proof test specification document. The main goal is to define the procedures to be followed by the maintenance operator so that the safety instrumented function works correctly after the tests are performed, and it ensures the reliability of the system. So these were the templates that I created in order to standardize our development. But there are also software tools which were proposed to optimize our resources. So first of all, I've created some upgrades in the CSpec tool. The CSpec tool is an in-house built tool created for creating logic specifications, and this tool is based on cause and effect matrices. So I made several upgrades in order to optimize its efficiency and automate it a little bit more. And I also added the Isographs reliability workbench to our safety lifecycle. This tool is a commercial tool available at CERN, and it helps in the design and engineering phase of the safety development. This tool is in accordance with the IEC standards and provides ways to create reliability calculations and hardware fault tolerance verifications. And these two are requirements of the design and engineering phase. So this tool is really useful for our team, especially because we already had the license acquired at CERN. So I propose several software tools, changes, and the creation of templates. And these can be used in the future functional safety projects at CERN. But they were also tested in a real functional safety project, which was developed by me for the SM18 cluster F, as I mentioned before. So for this project, I didn't have time to finalize the project. We just focused on the initial stages of the project. Actually, the first 4 stages, we are currently in the design and engineering of the safety instrumented system. The future phases will be developed by a future student or a future safety expert. So until now, I just reached the phase 4. So what was done for this functional safety project? The first step was to carry out hazard and risk analysis in cooperation with the process experts. In total, 42 hazards were analyzed. Some of them were already considered in the tolerable risk range, but all others had to have its risk reduced. Sorry. So for each hazard which had to have the risk reduced, we propose safety solutions, and this is the outcome of the hazard and risk assessment. So we have defined 19 safety instrumented functions, 3 basic process control systems, and 2 other layers of protection. Just a reminder, the safety instrumented functions have to be built according to the standards. The basic process control systems, they don't. And for each safety instrumented function, we created the requirements specification. Besides the most important requirements that were specified were the actuators, the sensors, and the signals that were used, but also all the other requirements were specified. The final phase, it is the design and engineering of the safety instrumented system, where I created a logic specification and I created reliability models to check the compliancy with the standard. I'll talk a little bit more about these 2 steps in the next slides. So for the logic specification, we used cause and effect matrices. For cluster F, we had a total of 481 digital signals and 12 analog inputs. I covered both the safety logic and the operation logic. So how was the operation of the test benches, the definition of test types, for example. And for that, I created, as I said earlier, cause and effect matrices. So I had to master this formalism in order to produce a clear and unambiguous safety logic specification. And here we have the example of the CIF16 cause and effect matrix. So it uses Boolean operators in order to create the relations between the different signals. And I also had to explain these formalisms for the process experts at cluster F so they could review the matrices, especially the operational matrices, and check if it was according to the system. Here we have another example of cause and effect matrix. And this is an important example because we see the signal here, the MTBF PC20 permit, is the power permit signal for the 20 kiloamperes power converter. So it's a critical signal that any mistake done with this signal can for sure generate an accident with the operators or to the installations. So these matrices, they need to be reviewed constantly by me, my supervisor, and the process experts. So we make sure that they are not, the requirements are coherent with the process. So this is the part of logic specification. Talking a little bit more about reliability models, I created reliability models for each CIF, and we verify if the probability of failure of the CIFs and the hardware fault tolerance, which is a requirement of the standard, if they are compliant with the necessary risk reduction. For this phase of the development, I had to master the fault tree analysis, and I also had to master the formulas of reliability calculations provided by the standard. So I had to learn a little bit to develop this part of the system. So yeah, basically this is what I wanted to show about the Cluster F functional safety project. So here are the main results I observed. So first of all, for the Cluster F project, the safety instrumented system is specified and designed following the standard, which gives the operator in the installations, let's say, we ensure that they are safe, at least until this phase of development. And the templates made the documentation more organized and standardized for my section. And this is especially useful in this Cluster F project because the Cluster F project is not yet deployed. So another safety expert or student will need to look to the documentation I generated and understand the project. So it's good that we have something standardized and organized so he has a clear understanding. And the tools made the functional safety engineering more efficient, reliable, and automated. So this was one of the goals of my studentship, and I think we somehow made contributions to this by adding the standards and both tools that I, let's say, one tool I modified and the other I added to our safety life cycle. Lastly, the templates, the tools, and the knowledge that we acquired can be shared with other sections at CERN. So this is important for my section that can share the information and present the results to the management, for example. So the conclusion is that the studentship was positive both for me and my section. From my section, the proposed enhancements represent a step towards the standardization and efficiency when developing functional safety systems. And for me, it was an invaluable opportunity to learn more about safety systems and also to work in such an amazing scientific organization and to acquire, uh, let's say, this engineering experience to deal uh, with unique processes such as the Cluster F project. So this was my presentation. I hope I was clear during this time, and thank you very much for attending the presentation.